To introduce Jim Bishop, actually for the second time. Jim spoke to us in August on the bristlecone pine. And today, bristlecone pine is part of Jim's avocation as a member of a very active member and leader in CNPS. He served on the statewide board. I have the pleasure to serve with Jim on the chapter council for the past few years. He's been active in the Mount Lassen chapter, but professionally, he has spent his career with CAL FIRE and is an expert on fire behavior. How does fire act? Fire, in some respects, has a personality, like people. It acts in somewhat predictable ways, and Jim is an expert on what those ways are, and was going to provide us with some of his wisdom today. So, Jim, we're interested in hearing about fire.
Okay, well, welcome to everybody. I'm glad you're interested to tune in. We necessarily cover a fair amount of ground in talking about this topic, wildland fire in California landscapes. And so it'll be a full program. I hope you can stay with us the whole time. And I really want to try and improve what I hope is the state of understanding of people about the fire problem, which often is discussed in very simplistic terms. And so I'm going to outline a couple of the things that I think are misleading and hope that by the time we're done this evening, you have a little better sense of it. So if you're all well aware of some very common media assertions about wildland fire. They often go something like this: fire has been excluded. Fuels have therefore built up to become a tinderbox or a powder keg. They're fond of some of those words, which leads to bad fires, the fire problem. And if only we would burn more, we would have a lot less trouble. Well, while there's some elements of truth in some parts of that, I think we really need a much more realistic sense of the problem than frequently is available on the media. So the wildland fire environment consists of the famous triangle of weather, fuels, and topography, all acting together to produce fire behavior. Subdivisions of those include aspects of the fuel and certainly important aspects of weather, like the wind and the relative humidity and the terrain, which way it faces, how steep it is, etc. I wish we had time to talk in some detail about every one of those, and we don't, but we will have, I think, time to focus adequately primarily on fuels and burns and what happens to the fuels that are subject to fire and what that leaves us with in terms of fire potential thereafter. So very straightforward explanation of fire's spread, because if you want to understand how factors affect fire spread, you have to have a sense of how it moves. It doesn't roll along the ground like a car or something. It's a process that's propagating, not an object that's moving. Heat is carried forward, indicated here by the kind of the blue left-hand end of the arrow, and it moves heat forward out of the fire into new fuel by primarily two mechanisms. One is radiant heat transfer, and the other is little jets of flame that directly contact the fuel ahead. The faster heat is transferred and the less the fuel requires to be heated up, the faster the fire will move forward. And it propagates through the fuel bed at a rate that we term the rate of spread, or for short, ROS in the fire behavior jargon. So things that affect affect the rate of spread, and that's something that's studied a great deal at the National Fire Lab up in Missoula. They build big fuel beds like this that are very uniform in their characteristics, and their properties are very well controlled. And then they measure rates of spread and intensity of radiation and all kinds of things. And in that way, develop models that are pretty good at simulating and predicting fire spread and helping us understand the factors that go into fire spread. And so that is primarily the spread of the flame front, but there's something else that's very, very important, and that's the flying embers, sometimes called firebrands. They really are the major problem for fire control and for the loss of structures, because they can propagate a great distance. Hot bits of everything that's involved in the fire can be carried up in the convection column and lofted out by the wind and land some considerable distance away. Single trees, if they torch out, meaning the flame rushes up through that tree, can throw embers and start new fires several hundred feet downwind. And when whole hillsides go up, they can start new fires well over a mile downwind, in extreme cases, several miles. So barriers you'd like to rely on to stop fire simply can't when it goes over the top. And it'll be something we talk about a little more later, but they are the primary ignition source for people's homes in wildland fires. You don't see them in the daytime, but they're always there. And once in a while, a nighttime picture captures just how many zillion firebrands there are. Any serious fire that's burning up through vegetation is producing them in copious quantities. They're carried downwind and they land hot, and they are a major headache. Some of the terms, rate of spread, we already covered that a little bit. That's how fast the flame front is advancing through the fuel. Intensity is a term that is used primarily to characterize the rate at which energy is being released by the flame front. And as a guide, the more rapid the rate of release of heat, the longer are the flames. So flame length is a parameter that measures that. And the more rapidly the fire spreads, higher rate of spread, and the higher the heat output of the fuel, those two things combine to produce the intensity. If you consume fuel faster, or the fuel has a higher energy output, both things will increase the rate of energy release. I use the term severity. You can talk about severe fires and so on, and that's okay, but it's usefully applied to the conditions that govern fire danger. In other words, severe conditions can produce intense fires. That's how we use those two terms. Crown fire, you probably have a good sense of what that is. It's fire that moves continuously through the crowns, the foliage of trees and or shrubs, spreading at least a relatively short distance through multiple crowns, as opposed to torching, which is just an individual crown igniting and going up independent of crowns around it. And scorching just refers to the kill of the foliage by heat generated by a surface fire. So wildland fuels, we're going to talk a lot about wildland fuels. And so their characteristics are such that they're divided into two broad groups: dead ones, and their fuel moisture is largely controlled by relative humidity, and therefore follows the same kind of patterns that humidity does, typically on short time scales, daily and hourly. As opposed to live fuels, which are the living foliage, they have fuel moisture which is controlled much more by the plant's physiological responses to the environment and the soil moisture that's available in the environment. And since plants don't like to get too dry on a given day, they're very good at controlling their moisture levels, and the major patterns are seasonal in duration rather than daily or hourly in duration. Fuel moisture, we've already used the term. I'll define it, and then I'll illustrate it in a minute with a diagram. It's the amount of water that was present in the fuel, whatever it is. If it's dry grass, it's dead fuel moisture. If it's live pine needles, it's live fuel moisture. It's expressed as percent of the dry weight of the fuel. So for example, if you had a 16-gram sample, you dry it out and now it only weighs 10 grams, you've lost 6 grams of water. 6 is 60% of the dry weight, 10 grams, so you'd call that 60% fuel moisture. And dead and live fuels coexist in virtually any fuel type you find, with the possible exception of just dead pine needle litter or dry grass. Here's some maritime chaparral, and you can see that the green leaves and the red branches are still living, manzanita. The gray branches are dead, so here's a case where live fuels and dead fuels are intimately mingled. This is a landscape that includes living pine trees, the foliage of which is all live fuel, and it stands in an area where much of the surface fuel is dead, either down dead woody material or dead grass or dead shrubs. So in any fuel, there's virtually both components will essentially always be there. So just to illustrate a little bit graphically, let the bar on the left stand in for the weight of some living foliage or live foliage. You pulled it off the tree, it's not going to be live much longer. And you heat it till it's dry, and you end up with dry foliage, and you weigh it. And the difference is the water that it lost. And the water is expressed as a percent of the dry foliage. So the water in this case is just a little bit over 60% of the dry foliage weight. And together, the water and the dry foliage are the components that were originally in the live foliage. All this water has to be pretty much evaporated out before the fuel will burn. So that's a big heat sink, and that's why it takes a little more heat to involve crown foliage. Dead fuel is also composed of the dead component and the water expressed as a percent of the dead component. One very important difference is these in live fuel moistures are typically several tens of percent, often 70–80%. In dead fuel, it tends to be about 1/10 of that. They are, when fires are fairly active, usually less than 10%. And as a rule of thumb, the dead fuel moistures march along with changes in relative humidity, and the dead fuel moisture is about numerically 1/5 of the relative humidity. So if the relative humidity is 30%, fine dead fuels like grass will have fuel moistures about 1/5 of that, or about 6%. So that's just a way of keeping in mind that the humidity is a major influence on fire behavior through its influence on the amount of moisture that the dead fuel contains. Live foliage is what feeds crown fire. Here's a picture of a moving crown fire front in the mountains of Wyoming, and it's like opening a pizza oven. You don't even see that this entire area of red is fed by a particular piece of fuel. It's just a huge heat producing process that's moving through, in this case, conifer forest, and producing heat from the forest floor all the way to above the treetops. Doesn't have to be tree crowns. This is maritime chaparral at Fort Ord that's burning as a crown fire. And this is sort of an interesting photograph that we had the opportunity to get from a helicopter looking down on the top of that moving crown. You don't usually get to see fire from that vantage point. But my recollection of this was it looked like you were looking into a volcano at molten lava that was churning below. It's a pretty spectacular view. So live fuel moisture, we mentioned, is seasonal in its variation. So across the bottom here, we've just illustrated basically a year from January through December. And if you were to sample in a plot of, say, manzanita or chamise or pine trees, and you measured the live fuel moisture throughout the year, it would increase from winter into the spring and into the early summer. Depends on where you are, how soon that happens. Down here, it happens fairly soon. In colder parts of the country, it happens a little later. But then the rains stop, the soil moistures decline, and the foliar fuel moisture, the live fuel moisture, begins to decline as well. And the red arrow here illustrates when it gets down to a level that typically allows crown fires to propagate. There is no single magic number, but it tends to be about midsummer in our country. And then it continues to decline on into the fall. And when it begins to turn back up again, depends on when we begin to get serious winter rains. Sometimes it stays down for most of the winter. In a particularly dry year, you still have the same basic pattern, but it will shift a little earlier and a little lower, so that this point of it becoming fairly flammable by July in the illustration here would back off into June sometime. So it doesn't change the basic pattern of peak, decline, and then low point in the fall. It just shifts it a little bit earlier and to some degree drops it a little lower, but we'll see some examples that say that it isn't necessarily that much lower depending on the previous month's rain. This illustrates the trend for old foliage. That's leaves and needles that have been on the bush or the tree previous seasons. You know, pine trees, for example, will hold their needles for several seasons, and many chaparral shrubs will hold foliage for several seasons. But they have new foliage, and it's much wetter. If you measure the moisture in new foliage, it starts out high, it drops, and by the end of the season, it matches the old foliage. And that is one point that is often overlooked. You often hear it said that we had a flush of new growth because of a rainy winter, and now we got more fuel and we're all in trouble. Well, not necessarily. The new foliage is the wettest foliage, and it really doesn't necessarily follow that a given shrub or tree is that much more flammable for having had pretty good winter rain. This is just a real world example. This was taken down in Ventura County of chamise. It shows the same basic pattern over a couple of years, and the average, it increases in the spring, declines rapidly with the onset of the dry season, drops down to its lowest values in late summer and on into the fall. And here they've illustrated with a red line the critical level for chamise, which is taken to be about 60%. It doesn't mean you can't have a crown fire back here if you have severe conditions and if you have pretty good dead fuel load to get it going, but it means that on average, this is about the point where you expect crown fire to be able to propagate continuously through, in this case, chamise. Now, this is kind of an interesting graph, and I'm going to take a minute to look at it. This is in an area southeast of Butte County, and they've measured through the year the manzanita moisture levels for 4 different years, the average and the low. And you can see it's higher in the early summer, drops down, a lot of variation here. But by the time you get to late summer and on into the fall, no matter how wet it was back here, everything is about the same level of dryness. So just take a look here. These years include 2 below average and 2 above average years, and actually span about a 3-fold range in winter precipitation. And yet when you get down here into the early fall, you can hardly tell these graphs apart. 2020 is in blue. It was a really dry year. 2017 was wetter, and the green one there, the brown one, 2019 was wetter, and yet they're still almost at the same place. So by the time we get to late summer and into the fall, virtually any year in California, you have the potential for low fuel moistures and the crown fire. This is one more graph that shows not the foliage, but the large woody dead fuel. This is dead fuel that's larger than 3 inches in diameter. Because it's larger like that, it tends to react much more slowly to changes in humidity, but it too is wetter early and gets considerably drier. No matter how wet it got back here, it's all getting pretty well dried out by the time you get into the fall. And both of those components are important in the severe high intensity fires we have. So an important threshold is where surface fire, which is primarily down here in surface fuels, transitions to crown fire. And some of the things that are important is relative humidity gets down in our country to about 20% or less. In the Southeast US, it can be up in the 30s, below 30 and about 35%. This dictates the moisture level in the fine dead fuels, and that's the kindling, and that's necessary to propagate and continue crown fire. And the live fuel moistures have to be low enough that the crown foliage is ready to burn. It can be over 100% in pines, which means that there's as much moisture in that needle as there is dry material, on down to 70 or 80% in chaparral, or you saw it there for Ventura County, 60% in chamise. Crown fire depends not just on those fuel moistures, but also on the vagaries of where and when intensity builds up high enough to propagate as crown fire. Here's a crown fire run that went up the hill. It didn't go sideways or flanking very much at all. It ran as long as it can maintain that intensity, and then it pooped out when it hit the ridgetop. This stand of trees over here is virtually identical to this one in terms of the moisture levels and the fuel configurations, and yet crown fire, when it was on a roll, propagated through here, but it didn't go that way, it didn't go this way. So it's a very nonlinear process. You have to hit an intensity threshold to have crown develop, and it often drops back down to the surface under what look to be the same conditions. So fuels, we group them into 3 different groups. Litter is all that stuff that litters the forest floor. It's the needles and the sticks and the pine cones. It's dead. That's in its favor as far as the fuel goes because it has relatively low moisture levels. But it's very compact, meaning there's not much airspace in between, and it's lying horizontally. Both of these things act against the rate of fire spread. Crown foliage is a nice vertically oriented fuel, and it's very open. So the configuration is favorable for fire spread, but it's the wettest fuel, so that helps limit the fire spread. Grass, on the other hand, is dead, so it's got low fuel moisture levels. It's vertically arranged. It's very open. It's optimal for propagating fire. And as a result, litter is the slowest fuel. Crown foliage is next, and grass is the fastest. I'll just look briefly at this. As effective wind speed increases, this shows how the rate of spread in different fuels increases. You can look at them as groups. For instance, this is crown fire fuel data, and no mystery to you, as wind speed goes up, rate of spread goes up. The groups are widely separated. The litter group is down here, the crown group is here, the grass group is here. So you can generalize fairly effectively, considering different fuel types and the fact that they will propagate at different rates in a particular wind. Just a little cartoon to illustrate that. Litter on the scale, if you gave it a 1, will move at, we'll call it number 1, relatively slowly. Crown fire under the same conditions would propagate about 4 times as fast. Grass fire about 15 times as fast. So about a 4-fold jump as you go from the slow fuel to the medium fuel to the next fuel, if everything else is equal, the wind and the slope and so on. Wind is really important. It varies in many, many different ways. It varies over the terrain. It varies with the vegetation and the flame heights above that vegetation. It undergoes daily patterns. There are large-scale winds that come with downslope wind systems, fern winds, the sundowners, the Santa Anas, the east and north winds we have here, frontal winds. There are winds that come out of thunderstorms, and they contribute to the seasonal patterns of the fire environment. And I wish we had time, because it's an interesting subject to do it in detail. We'll hit a couple of general points that help us understand the year-long pattern in fire behavior. Wind varies a lot over the terrain, and a really good clue is where do they put the windmills? The wind is highest on the upper windward slopes, and over the tops it's much less on the backside and the lower slopes. As a generalization, here we've illustrated just kind of a schematic of a couple of hills in cross-section, and the length of the arrow indicates the wind speed. So if the wind speed over the ridgetops is this much, call it 20 miles an hour. On the windward slope down low, it'll be about half that. On the top third, it'll be up to ridgetop wind speeds. As it goes over the top of the hill, it gets very turbulent and it slows down. When it hits the next slope, it begins to pick up again over the top. And if you average these things, it's about 3/4 speed on the top third backside and down to 1/4 here. So you can see just between here and here's a 4-fold variation in the effective wind speed. And that's one reason that fire makes strong runs upslope and slows down on the lee slopes. How thick the stand is has a lot to do with it. Here, monitoring the wind in a fairly open stand of trees, the wind speed was about 5 miles an hour. Nearby, in a much more dense stand of trees, it was down to 2. So the vegetation itself affects the wind speed. More open sites, as you'd expect, experience higher wind speeds. The level of the flame above the ground affects it. At the ground, the wind speed is 0. And up at a level of, say, 20 feet, we'll call that 1 on the scale. That's the winds that push crown fires. Down here at grass fire level, which is about your eye level, if you held up an anemometer and looked, it's about 3/4 of that. And down here in the lower foot or so above the ground in litter fire, it's about 1/4. So there's a large variation in the wind acting on the fire, just as a function of what level the flames are. And we can just take a quick look at how those things act together. Let's imagine we consider a hillside here where crown fire is burning up the hill. And just looking at the last diagram, the wind on the lower slope is less, the wind on the upper slope is more. It's going up the hill and it gets to the top, it goes over the hill, loses its momentum and stops being a crown fire and starts backing down the hill against the slope in the litter, experiencing considerably reduced winds. So there's a dramatic change in the fire behavior from one side of the hill to the next. It can easily account for 100-fold change in the rate of spread. This is handy for firefighters, but if you reverse it and put the hill over here and let it back through a drainage and run up the other side, that's not very good because you can still see the same 100-fold change in rate of spread. Okay, now putting some of the ideas about the fuel condition and the wind together in understanding the daily rhythm of fires. Across the bottom here from midnight, 6 in the morning, noon, 6 in the evening, midnight the next night. The blue arrows indicate the wind speed and direction. So it's fairly light, and let's say it's down slope. And then daytime comes, it starts to blow up slope, and it strengthens so that in the afternoon you get the biggest winds, and then the sun goes down and you start getting weak down slopes and then stronger down slopes. So there's the wind pattern through the day when the dominant influence is just the daily up canyon, up slope, up valley winds versus down slope. Let's add to that the fuel moisture. Humidity rises with lowering temperatures and then declines with increasing temperatures through the day. And remember, humidity is about fuel moisture is about 1/5 of that. So this curve shape still can represent fuel moisture. It's at its minimum in the afternoon. So this is the time of day from late morning to early evening when fires tend to be the most active. If you don't have some predominant wind, like a strong downslope wind that overrides that at night. But it's very, very common for fires to lay down at night, as they say, and become active and take off in the afternoon. And it's because this is where the fuel moistures are lowest and typically the wind is the greatest. But those big wind systems are very important. And a really important one for us is when wind blows perpendicular to the mountain range and rapidly down slope. So when we get north and east winds, they're essentially a type of downslope or firn wind. Even though this is a bit of a schematic, it doesn't really look quite like the Sierra Nevada. This is the general idea. Probably one of the most important wind systems for producing destructive fires in California. Whatever you call them, they occur throughout the state, in the Coast Range, in Southern California, and in the Sierras and in the Cascades. We have our own rather special version of this here. This is the North Fork of the Feather River, and it goes around what's called Big Bend. It has a huge air shed, over 2,000 square miles of air basin upstream that's producing cold downslope flows all night long, and it comes pouring down the Feather River Canyon, and not much of it makes the turn at Big Bend. A lot of it goes right on over through Yankee Hill and Concow, and a little further over here right down into Paradise. There is a weather station up here at Jarbo Gap that is famous in the National Weather Service for frequently producing the strongest winds along the Sierras when we get the northeast winds. So some of our very worst fires, certainly the Camp Fire and many, many fires in Concow and Yankee Hill and down here at the Poe Power Plant, have been driven by those winds. The mechanics of it are very similar to the firn winds that affect the whole mountain range. So we'll put that together and think about seasonal patterns. This is kind of schematic, but it captures some of the main aspects of it. So let's consider going from spring on into the following fall. We've talked about this. Live fuel moisture rises when moisture is plentiful. The temperatures are warming. The plants are all happy. They're putting on new growth, but it begins to decline. And by midsummer or so, you're down to levels where it'll burn pretty well. It continues to decline and level out and reaches its minimums on through the fall. The wind driving pressure systems tend to be fairly strong in the spring. They decline in strength into the summer and are relatively weak in the midsummer. Then they begin to strengthen in the fall. The pattern that's produced just by the daily upslope flows and the nightly downslope flows, we'll call it a diurnal pattern, it tends to be fairly strong in the midsummer. And add to that, we get our thunderstorms whenever we do from about mid-July into early September. The Bear fire was ignited in mid-August, right during thunderstorm season. It did not run very hard. It was back at the time of the year when we had relatively weak pressure systems dominated by up canyon, down canyon flows, but not really high wind speeds. But by the second week of September, it took off. We were starting to see the increasing strength of those mid-latitude storm systems. They first usually come into us dry, but plenty windy. And that was an extremely windy time, and it took the Bear fire, and we're going to look at that pretty carefully here a little bit later, and ran it very hard. The Camp Fire occurred in November. All of these occurred when the fuel moistures were way down at their minimums. The Camp Fire occurred again when there was a lot of strength in the mid-latitude storm systems that were dry but were windy, and the result was it went ripping through the town of Paradise. So I haven't told you anything you don't know here, but just to mention a couple of points, because structures are very vulnerable to wildland fire, and it's important to know how to reduce that vulnerability. Some of the things that add to the risk, flames have to be within about 20 meters, or at worst 30 meters, to actually ignite a structure directly by crown fire. Crown fire typically burns out most of it right at a given point in about a minute. You can get direct flame contact at about 10 meters. That's a little over 30 feet out, and that certainly can set your house on fire. But by far the most important ignition source are embers that ignite fires by falling on the structure or in the yard or through openings. And it's just like lighting a match and dropping it and hoping, watching it spread to your house. Homes burn mostly from flying embers or from flames that approach the house and then spread through what you could call fuses, like a crack in the sidewalk with some dead grass growing out of it, or just a flower bed that has pine needles built up in it, or whatever. And homes can burn hours or days after the wildfire passes. I know of one case on the, forgot the name of the fire, but it burned up out of Redding, and a fire was discovered under the floor in a house 3 days after the passage of the main fire front, where embers had blown in through an unscreened opening. It was a fountain fire, an unscreened opening in the basement wall. So this just summarizes something you can get through your fire safe councils. It's really a helpful, practical guide to how to protect your home. The ignition zone within about 10 feet or so, there should be nothing that can convey fire to your house. And one way to mentally test this, I wouldn't recommend really doing it, is just imagine throwing lighted kitchen matches everywhere around your house and ask which one of these under severe burning conditions could spread to my house, either on the house because you've got leaves in your gutters, or a box of kindling out on the deck, or bark mulch in your planters like this. I mean, this is wonderful stuff for keeping the weeds down, but you couldn't design a better fuel bed to ignite from embers that fall into it. The next zone out, you really want to continue, you want to treat that by removing bushes and trees so they're widespread, by limbing them up. The whole idea is you don't want fire to be able to torch out anything in here and kick embers over into your house. And you also want to reduce the intensity so firefighters can operate here and they're not going to be run off because the fire's too severe. And in the outer zone that goes on out, beyond 100 feet, you want to reduce fuels and just kind of let that transition to the unmodified natural fuels beyond. And if you do that, fire intensities decline considerably as they approach the defensible space zone. People can still operate here. You don't have anything in the home ignition zone that's going to receive a firebrand and ignite your house. So one of the things I want to talk some about, how many minutes down?
No, you're fine.
Boy.
That's just down. It's not.
Okay, good. You hear it all the time. Well, we got to get rid of fuel. We got to burn it. Well, I want you to understand that that's only half the story, part of the story. The foliage of living shrubs and trees is burned or scorched, but most of the mass of that wood is not usually consumed. It's frequently killed, at which point it becomes a dead available fuel. For conifers, just scorching the canopy will kill it. If you see that all the leaves on a pine tree after a fire goes by are a faded dull green and gradually turning brown, that tree is dead. Now, this is an example in an arid land, shrubland on the other side of the Sierras, in which a fire that occurred last August did a great job of consuming the fuel. You can see the unconsumed fuel back here. You almost never get that complete consumption. This is because it was so dry. Those shrubs were just covered with shredded dry bark, hadn't burned for quite a while. Normally, you don't get anything like that. Normally, you get something more like this. This is a patch of manzanita right on the edge of an opening next to the bear fire. So the bear fire burned this half the bush, didn't burn this half the bush. What you see here is about 10% of the plant's mass is foliage and is available to burn, leaving behind the other 90%, which is now going to be dead sticks and scorched leaves. And as this dries out, as far as the next fire is concerned, almost that whole manzanita bush is now available fuel. So you went from 10% of this being available fuel to almost 100% being available fuel just by burning it, but incompletely burning it. A conifer forest example of the same thing is here in the Jeffrey Pine Forest. Very open forest, hardly a lot of stuff built up on the forest floor, but this burned really quite well in the crater fire in the year 2000. A lot of the trees were killed, scorch killed, and they stood there for a number of years. And then we had some big strong south winds and they all blew down. So now you got a lot of large woody fuel on the forest floor, and shrubs and trees are starting to come back up through it. So this surface fuel bed has more fuel than it did back here before the fire went through. This is a picture from the Wall Fire, Eastern Butte County. And this used to be an oak woodland with lots of green shrubs, green leaves, some gray pines and live oaks. And now almost everything in the picture is dead. And a lot more grasses here because, as folks who think about plants know, one of the things that limits the growth of plants in the lower levels is lack of light. Well, once you burn all the crowns off or you scorch them and the leaves and needles fall off, a lot more light reaches the ground. And in response to that, you get a growth of things like grass and small shrubs that's pretty profuse. This is a picture from near Feather Falls and the Bear Fire. And this is under a stand of conifers. Every one of these trees is black all the way to the top. And what you see here is all the needles that were scorched, killed, and they fell on the ground. So this fuel wasn't consumed as crown fuel. It is now dead and become a surface fuel as part of the whole fuel bed. So it's not quite as simple as we simply burn things and we get rid of fuel. Yes, you get rid of some, but you also alter the fuel bed in ways that frequently increase the total amount of fuel that's there. So natural fire is certainly been part of the system for a long time. It can be very beneficial, but it's not quite as perfect an operation as is frequently said to be. So I want to go over this a little bit and look at some fairly realistic examples of natural fire. The mean fire return interval is one of the terms they use to mean, on average, how long is it at a given point between fires occurring there. It's very low in places like dry yellow pine forests, such as in Arizona, where they have lots of lightning. The mean fire return interval increases when it's wetter. Also, if it's very dry, you have sparser fuels and higher elevation systems. And there's a huge amount of variation. I read one report of Ponderosa pine forest in Wyoming, and the mean fire return interval was reported as average 13, but ranged from 3 years to 97 years. In fact, there are often questions raised about the sampling methodology, depending on these, you know, you can find fire scars, but then you got to make assumptions about how widespread those fires were. And you can get some disagreement even among the experts as to what the mean fire return interval really was. An important point I want to get at here tonight is it's very different in different fuel systems. And sort of a bottom line is when burn conditions are severe, intense, fast fires can occur in any grass or crown fuel type. They can occur in litter. They won't be quite as fast, but a fuel bed is never immune to rapid fire spread under severe conditions. So let's go through the different fuel types one at a time. The Ponderosa pine forest is in the Pacific Southwest. A few years to a few tens of years, typical mean fire return interval. The understory recovers in a few years, maybe 5 years. Interesting point, as grasses were grazed early in the settling of the West, it removed one of the fuels that helped these periodic low intensity fires, and they actually got fewer of them. In the Central Rockies, the reported mean fire return intervals run up to centuries, and some parts of the burn and some fuel types, especially lodgepole pine, stand replacement crown fire is the norm, not low intensity fire. The coastal forests of the Pacific Northwest can be centuries to a millennium between burns in a given area. Even here with a lot of moisture, if you have really critical fire conditions, you can have some huge burns like the Tillamook burns and even the burns in Oregon this year. The subalpine forests, which are way up there, very discontinuous fuels, lower oxygen concentrations, although it's hard to know how big a role that plays, and centuries to a millennium are more typical of the return intervals up there. So the ideal is conifer forest like this. This is Jeffrey pine forest, nice mature trees, fairly widely spaced, light fuels on the forest floor. And with good fuel on the forest floor, they are a great place to have low intensity fire propagate, remove that surface fuel layer and leave the crown fuels undamaged. That works when you have two conditions. One is, as in this picture, no limbs well up the tree. So the foliage is well elevated above the ground, many feet, many tens of feet in some cases. And down here you have a fairly modest layer of fuel that's not going to burn too hot. So you have to have clearance between the surface fuel and the crown fuel, and the surface fuel has to be capable of propagating low intensity fire. Here's an ideal surface fuel. This is long pine needles, in this case Jeffrey pine and pine cones. Short needles are more compact. They don't burn near as well. Some of the sclerophyllous leaves of things like live oak aren't so hot either, but the yellow pine is ideal for producing a nice surface fuel bed. And when you have that and you have not too steep a country, you can have a fire like this propagate through. You can see that it's consuming the surface fuels and it's not bothering the crown fuels above. That's the ideal low intensity fire kind of example. But the real forest isn't all like that. A lot of it is quite steep. This doesn't look as steep as you'd realize it was if you tried to walk up it. Fuels vary a lot. There's rocky areas, there's thick areas. And so it's not somewhere that it's going to be easy to get that ideal low intensity burn that doesn't bother the overstory and cleans up all the flammable fuel. And the fact that the low intensity fire usually spreads slowly means you got to have a lot of small fires to clear the area that you'd like to clear. Here's an example from the Feather River Canyon wall that illustrates a couple of things. For one thing, this fuel is quite varied. Over here, it's a lot of grass under gray pines. There's areas of dead forest. There's areas of this kind of shrubs. There's areas of that kind of shrubs. It's very steep. That would be tough to do a nice control burn on. And when you do a control burn, you have to consider, when will I do it? if you do it way late in the season, it may just get rained on before it gets very far. If you do it too early, you may get a siege of strong winds that blow it out of control. How big does it need to be to get to the average return interval that I want? How long is it going to last? The smoke production. And if you're going to go out and actually do the operation as a purposeful control burn, what's the cost? What's it going to cost in terms of crews? So it can be done. It can often be done to benefit, but it is not a trivial operation to make it work in all these difficult terrains. I'm not talking about just, run around with a drip torch on the floor of Yosemite Valley someplace. That's pretty easy. But the real world of steep canyon sides and so on throughout the mountains of California are a bigger challenge. And one pretty important point is that we have many fuel systems in California. The kind of generalizations you hear from the media and even alleged experts are frequently just mentioning this idealized conifer fuel type and the things that you can do there. But here you see in different colors all these different major landscapes and fuel types in California. And even within the conifer forest, which are shown here in dark green, there'll be a lot of variation between the Southern Sierra, relatively dry pine forest, and the northwest part of the state, relatively wet Pacific coast forests. So I want to take a look at examples from these several fuel types. Ag land doesn't burn much, wetlands don't burn much, cities don't burn much. So this covers the half dozen or so major fuel types you see here. Chaparral and shrubland. Mean fire return interval is decades to over a century. Takes about 20 or 30 years to recover. Now, the old wisdom was that chaparral was a fire-dependent species. That burn it, it's good for it. That's true, but not if you burn it too often. Frequent fires at about 15 to 20 years or less convert it to a weedy grassland, and much chaparral in Southern California has been lost to that process. But it can reburn 3 years after a fire. So if you need to leave it alone for 20 or 30 years, most of that 20 or 30 years is going to be perfectly flammable. If you try to burn it often enough to make it so sparse that it can't burn, you'll just get rid of it. And you don't underburn chaparral. This is maritime chaparral. That is a beautiful fuel bed, but not one that you underburn. Little tiny leaves, you might get something to smolder in small patches, and even if you did, this would still be ready to burn when the next high intensity fire came by. This is coastal scrub, same story. You don't underburn this. Keep in mind that picture, conifer forest with an elevated mass of foliage in the crowns and surface fuel that will carry low intensity fire continuously. You don't have that separation in either of these fuel types. You burn it often enough to significantly reduce the fuel, you'll basically get rid of that shrubland and turn it into grassland. Grasslands, tough to know the history because they don't have these nice sentinel trees that tell you the whole story with their fire scars. Mean fire return interval, some areas probably years, some other areas probably decades. It doesn't take too long for the system to recover, not to grow a new crop of grass, but to recover for all those other things that died in the process. If you burn it a lot, you tend to get more annuals over perennials, and annuals are frequently invasive, and the perennials are the natives that we're losing. This is a nice picture of cheatgrass in the Great Basin. It's a introduced grass, highly invasive, great fuel bed. This is how grass burns. This is just annual grasses in our Sierra Nevada foothills. It burns great. Remember, that's the fuel that's dry. It's vertically arranged and optimally compacted, so it burns great. However, you don't get rid of it except for that year. It'll come back. So there's no fuel reduction in burning grass except you burnt the grass, but it's going to be back the next spring and ready to burn again. Foothill woodlands. Again, the history is not terribly well known, highly variable in terms of the things that do grow there. Mean fire return interval could be years, could be decades, and really varied in form. The classic blue oak savanna is scattered oaks with grass. That's an easy fuel type to burn. But an awful lot of not just our Sierra Nevada foothills, but in the Coast Ranges too, are host to live oaks, foothill pines, toyons, manzanita, tan oak, and all kinds of shrubby things and shrub-like trees that do not resemble a conifer forest. Here's an example of the idealized blue oak savanna. You know, you can underburn that just fine, but again, the fuel load would return as soon as the next spring came. But something like this, which is in our lower Northern California foothills, is nothing like the ideal of elevated crown foliage over a continuous, easily burned surface fuel bed. And here's an example from near Lake Oroville, in which the foothill fuels have conifers in the form of grape pines, a lot of chaparral shrubs, grass, and as one example, an area containing these fuels near Oroville State Park was control burned. It took 3 burns, and between every burn, they had to do a lot of mechanical manipulation to remove things and pile them and do some supplementary burning and so on. It was really difficult to do. You end up with a nice stand for a while, but it rather quickly fills back in, so you really haven't bought much in fireproofing it, and it's exceedingly slow and expensive to do. The grass in these systems returns every year. Remember, if you let the light in, a lot of things will grow that didn't grow there well before. Mixed fuels are really difficult to underburn. You'll be torching out the gray pines before you even get the surface fuels to burn as well as you want. They're tough to underburn, and they quickly return. The Pinyon Juniper woodlands, which are a more prominent fuel type than we're necessarily aware over here, but as soon as you get over to the other side of the Sierras, they are the dominant conifer woodland. Fire return intervals of order a few centuries. Notice these numbers are fairly high. In most fuel systems, the return interval is so long that fire control hasn't really impacted that all that much. To get it to propagate in these Pinyon Juniper woodlands, you need some good grass or a pretty good wind. The rule of thumb for a lot of people I've known who did burning in the Great Basin was 15 miles an hour. When you burn it, you'll kill the trees and most of the shrubs. Full recovery can take a very long time. Cheatgrass, which is an invasive grass, has completely changed the fire regime and the ecosystem, converting it to almost pure stands with fire intervals of less than 10 years. So the act of having natural fire because of the invasion of those grasses has produced a completely unnatural result. And here's some illustrations of that. Here's Pinyon Juniper. This is the juniper, the pale yellowish green. This is the pinyon, the sort of gray-green. You can see that there's no nice handy layer of needles on this forest floor. There's scattered patches of grass. The crown foliage goes all the way to the ground, so obviously you don't have a separate upper and lower fuel bed that allows you to underburn. You either burn this or you don't. And when you burn it, this is what you get. This picture was taken right across the highway from this picture on a side that has suffered many more burns. You end up with a bunch of dead trees in a sheet of cheatgrass and a few resprouting shrubs, highly flammable fuel bed. Yeah, you eliminated some fuel, but actually the available fuel load here is greater than it was over here. In this particular case, this mountainside used to be all like this. The Pinyon Juniper woodlands were essentially the forest of this country. And there's an irony in this picture. This mountain range is called the Pine Nut Range, named for the pinyon pines that covered it. And now you can see the pinyon pines are just remnants. This has happened within the last 10 to 20 years. All this other stuff is shrubs and cheatgrass. And if you look up and down this range, you see the same picture over a number of miles. So Pinyon Juniper woodlands are not practical to underburn. The hotter burns destroy the woodland. And in the case of the Pinyon Juniper woodlands, the invasive cheatgrass just takes over everything. Southwest desert landscapes didn't used to be a place that hosted much fire. Very rare in the natural areas. But now, because of invasive grasses, it's much more frequent. Here's a picture showing those invasive grasses in a desert landscape. And it can carry fire. In this case, here's a stand of Joshua trees that have been burned. because the continuity of the surface fuel due to the invasive grasses. So you're not going to profitably introduce natural fire into a system that's altered in the desert. How are we doing?
Okay.
So it's often commented, we have a big fire and somebody says, well, that area hasn't burned for umpty years. A comment from an official after the rim fire outlined in red was a century of fuel buildup. But this is a map of previous fires. Many major fires burn areas previously burned. Some of those burns may have actually increased the fuel load, but the popular assumption of it is that if you've had previous burns, you have less fuels. Conversely, if it hasn't burned in a long time, you must have a lot of fuel. Well, most of the rim fire burned areas that had been burned in the previous 20 years or so. And in some of the other areas, they had been logged and the plantations introduced. So it simply wasn't true, as was proclaimed at the time, that the rim fire did what it did because fuels had not burned for a century. This is an interesting picture. The black outline is the Tubbs fire 3 years ago that tore into the subdivisions on the side, on the outskirts of Santa Rosa. It ran in almost the exact same footprint as the Hanley fire from the 60s. So this too had hosted previous fire. This is a map, a partial map of Southern California, and this tallies fires only between 1950 and 1912. You can see that almost the entire area has burned multiple times. That's the outline of the Thomas fire 3 years ago. And you can see that virtually all of the Thomas fire was burning in previous burns. And our very own campfire, the perimeter is in red. This is the town of Paradise. It would now show as a burn. That fire took off and got up to a very high rate of spread at a huge wall of fire by burning through this area, which has hosted not just the 2008 fire, but several fires before that within the last 10 to 20 years. This was immediately condemned as forest mismanagement, but there is no forest here. Those fuels were downed dead wood, dry grass, dry shrubs because of the previous fires. And that fire tore through here like crazy, flew into Paradise, bombed them with spot fires, burned all kinds of houses up, killed 80 some odd people, and took off out the other side right through the Humboldt burn. So it's simply not true that these major fires are all burning in areas that just haven't burned forever. This is Plumas County and a little bit of Northeast Butte County showing previous fires from 1900 to 2015. And I'll show you the footprint of the Bear fire. It's here. Started back here, actually started in an area that had previously burned. A lot of this wasn't recently burned. A lot of the community damage was up here in areas that had previous fires. And an interesting thing, which we'll talk more about, is the whole center of this burn wasn't previously burned, but it was previously logged. This is private timberlands, and you can see here that it is not continuous forest. This is a mosaic of everything from recent clear cuts to plantations to mature forest. So the Bear fire did not run through a huge area of accumulated fuels. They had either been burned or they had been removed by logging. And fire size is something that is often used as a gauge to decide, are things getting worse or better? Talk about average acreage increases and record numbers of acres burned and so on. But fire size reflects many things, not just fire intensity and fuels in whatever state of building up they may have been. And I'll talk about some of those factors. And I'm using an example here of the Thomas fire, and I'll show you how it became a big fire. At the time, it was the biggest one, due to these things. Fuel moistures, it was late season. You've already seen the patterns. You now know what it means to be late in the season, meaning beyond midsummer in Mediterranean climate fuels. They're dry. The humidity, less than 20%. That's a pretty good rule of thumb. Well, the humidity on the Thomas fire was down to 1% and 2%. The live fuel moistures were 53, which is extremely low. Winds over 20 are usually big trouble. The winds on the Thomas Fire were up to 40 miles an hour. Threatened homes, which means that there's a diversion of fire resources to structure protection. And this is often the case, second fires or multiple fires, because you simply can't adequately respond with suppression forces to catch those things if the resource is all drawn down by the first fire. Another thing that contributes to large acreage is large burnouts. And that's been accelerated by an evolution of the fire management philosophy of the federal agencies, where they think sometimes they want to actually burn more than they might have to. And so they will do very large firing operations that may produce a lot of acres that didn't necessarily need to burn under the influence of the wildland fire. Resource drawdown. If you can't muster a decent response to a fire, you're not going to contain it under severe conditions. And of late, they're fond of lumping these things into complexes. It might be 2, 3, 4, 6 fires, and then give the total acreage and talk about what a huge fire that was. So this is a map of the Thomas Fire early on. This is the city of Ventura down here. This is the Santa Clara Valley, Oxnard, and the coastal plain and so on are here. This is the Ojai Valley. The Thomas Fire ran under the influence of northeast winds almost all the way to the coast. And you can see by these division lines, this is about where they thought they were going to stop it. But there's one other thing in this picture. That is a second fire. It occurred within, I think, not even an hour, but within a short time of the ignition here, they had a fire over here that received almost no response. This fire is the thing that propagated into the Santa Ynez Mountains and on around the Ojai Valley and took off towards Santa Barbara. So the second fire and the reduced resources all added up to being the thing that pushed the Thomas Fire from being something like this, a major fire certainly, to being what it became, which was to roll not through just here, but all around Ojai, through the mountains and on all the way up into Montesino and Santa Barbara. Another thing you see in this picture, this is active fire line in red. It didn't burn in this funny pattern all by itself. That's a firing operation that's being conducted in a wilderness area by the federal agencies because they wanted to just not go in there with equipment and they wanted to introduce some fire in there, which is fine. However, it adds a lot of acres, and it was not the only wilderness area that was treated that way. So that's one more factor that will add to acreage that doesn't have anything to do with intense fire behavior. Now, when conditions are severe, you don't need heavily built up fuels to have damaging fires. This is a picture from last summer outside of Oroville here on about a 20-mile-an-hour wind day. Fire got going in grass, tore off across the field, and ran into a subdivision and burned down 4 homes. So this was as light a fuel as you can have. But under severe conditions, with people's property exposed, you can have severe fires with very costly damages done. So another example of how even in light fuels or fairly natural fuels, you can get severe fires. This is looking down at Bald Rock Road. It was before it was impacted by the Bear Fire. You can see several things here. I'm going to show you a picture on this side of dense conifer forest and on this side of more open conifer forest, and then a picture of this logged area that was very open. First, the forest on the right, it was a forest that was pretty thickly vegetated. It had been logged sometime in the past. It had a lot of relatively small to medium-sized trees close together. On the other side of the road, it was much more open. There's not tons of undergrowth here, and yet all of these trees are black to the tops, and all of them are scorch killed, and all the surface fuels have been removed. So even though this was much more open, it's still, under those conditions, burned. And this is that open area that had been cut, clear cut. All these stumps are burned. All these trees are dead, some crowned out, some just scorch killed. But even being this open under those burning conditions did not keep this area from being burned. So we'll talk a little about the Bear Fire. That was certainly one that amused Katie and me and everybody around here for a while. It moved 30 miles in less than 20 hours on one continuous run. The bear fire started from lightning in the middle of August, back there during the peak potential time of monsoon moisture moving into California and creating lightning storms. It did not get put out for 3 weeks. Strong northeast winds occurred on September 8th. The fire escaped. And when it got on a roll, it ran in less than 20 hours, 30 miles, all the way to Lake Oroville. And one of the first things that was said was, well, there you have it, mismanaged forest. That's code word for you put all those fires out and you let all these fuel build up, and now look what happened. But here's what it ran through. It ran through some dense forest. Yep. Also through open forest. It ran through clear cuts. It ran through timber plantations. It ran through shrub and chaparral lands. It ran through oak woodlands. It ran through foothill mixed fuel woodlands, and it ran through fuel breaks and old burns. And none of them slowed that fire down or stopped it. And I'm going to show you pictures of those things. This is a map. That's the Claremont fire. This is the Bear fire, about 3 weeks into their fire histories. This is the middle fork of the Feather River right here. The Bear fire at this point is backing on its own. There's no suppression action being applied here. Backing down to the canyon bottom, some firing operations have been done up here, and that's the edge of the firing operation. But this is unmitigated wildfire from the original lightning strike back here that gave rise to the Bear fire. This is the nighttime infrared flight before the fateful morning of September 8th. Let me go back to here. It was noticed that by about 8:30, evident on the infrared satellite, right down in here was a spot fire across the river. And you remember what we talked about earlier? One tree torching can throw spots several hundred feet. That's plenty to get it across the river. And something did. So it was reported down here. It was verified that it was there. By mid-morning, it was coming out of there, and nobody was going to stop it. Here's a photograph taken by a friend and former colleague who was on the dam of the Little Grass Valley Reservoir with a picture of in the early afternoon of the Bear fire as it's pushed by strong northeast winds in only partway through its 30-mile run. Remember, it ran through all this country that had much of the fuel removed by logging operations. And here's a series of photographs that are going to show the variety of fuels that it burned through. Dense forest stands, that's the picture I showed before. Yep, it sure did. Open stands, it also burned through them, killed the trees and the foliage, even if it didn't consume it. It burned through young plantations. These are small, widely separated trees with almost no fuel on the forest floor. It burned through more mature plantations with widely separated trees and almost no fuel on the forest floor. Many of these trees were scorched, and you're starting to see the needle fall. It burned through clear cuts, turned all the stumps into charcoal, and burned all the surface fuel, even though there was no forest there to burn. And when it got down in the foothills, it burned in the areas that are mixed chaparral and shrub and trees. It burned through the Ponderosa fire burn, which was only 3 years old. It didn't burn everything, but it burned through it nonetheless. And when it got down in the lower foothills, it burned hillsides that were primarily woodland grass. And as you can see by the faded color of these conifer tops, they were all scorch killed, even though they were not consumed. So it burned through a wide variety of fuel types, not just dense forest, certainly not just mismanaged forest. And under those conditions, there was no fuel you could put in front of it that it would not burn right through. So fire season 2020 is a good example of the fire problem for bad fires. And so let's go through some of the factors that made it that way. Okay. It was a very dry year, driest it had been in decades. Probably the last time it was this dry was 1977. But remember, those graphs, you don't have to have a record drought year to have dry fuels in late summer and early fall. This was critical. We had a very unusual lightning outbreak in mid-August with over 600 new fires. I have spoken to former fire meteorologists from Reading who contacted their colleagues there, and they all agreed that this kind of incident, you didn't see it, but maybe every 10 or 15 years in California. And because there were hundreds of new fires, we had a severe firefighting resource shortfall. However, I will say the vast majority of these were picked up. It was only about 10% of them that kept going as major fires. And they lingered into early fall. And remember the graph, they occurred back during the midsummer when the wind systems aren't that strong, but they hang on until early fall when the fall weather systems and the strong north and east winds could develop. They burned for weeks, and they, when pushed by wind, did a lot of damage to communities. The glass fire over near Santa Rosa was destructive. The bear fire was destructive. The creek fire was destructive, and then the complexes in the coast ranges were all destructive. And so often the immediate explanation is, well, fuel buildup or climate change, but this list does not include either one of those. You don't need fuel buildup or climate change to understand why we had a bad fire season in 2020. It doesn't mean climate change is not occurring. Clearly it is, but you have to think carefully about what role it may have played or not played in those fires. So the common denominators, these are the things you see all the time associated with bad fires. Dry fuel, both because of low humidities, which dries out the dead fuels, and seasonal and maybe drought enhanced drying of the foliage. Wind, strong winds, many ignitions, so that you have a big resource shortfall. And another thing that plays into resource shortfall is a lot of exposed homes, which calls for lots of commitment of resources just to protect those homes. These things are frequently correlated with bad fires. We have heavily built up fuel areas day after day after day, and sure, you can get a bad fire there, but many fires occur there that are quickly put out. So the consistent correlates of serious fires are the weather conditions, fuels that are dry enough to carry fire, complicated by lots of ignitions, lots of values at risk, and inadequate resources. So something's on top of my words there, but anyway, I hope you can see this. This is just kind of a really simple summary of fire behavior. It won't surprise you. I'm sure your common sense tells you the same thing. If it's dry and windy, it can burn. The drier and windier, the better it burns. And I'm going to show you an example here. This is a fire. You can see that is the High Sierras covered with snow right there. This is over between Mammoth Lakes and Bishop. It occurred on February the 6th, the middle of winter, at 6,600 feet. But in spite of that, it was dry and windy. And as a result, even in a relatively distributed subdivision, 40 homes were destroyed. So you don't need massive amounts of fuel. You need severe conditions. Even in the middle of winter, you can have an extraordinarily destructive fire. The fire problem, that's really the point I hope you'll think more about. Don't take everything I said for granted, but at least begin to think about it. The fire problem is not simple, and it has no simple solutions. That doesn't mean we can't make good progress in some ways, but it does mean the simplistic notions that are afloat out there aren't the solutions. The problem is extensive. Nationally, there's 74,000 more fires burning 6 million acres. That's a 10-year average. In California, we have almost 10% of those. Our average acreage, which has been about 700,000, probably up a little after the last year, about 90% of these are human caused. So there's nothing like natural fire in this mix. It's a huge imposition of manifold more ignitions on the system than ever was done naturally. The time distribution and the intensity fires is skewed. They don't occur just during the lightning season. They're occurring during the late fall when the wind blows hard. And there's a whole lot of valuable property in the way. So the fire problem is complex. And the solution is also complex. burning as part of it is a fine idea. Burning as all of it is an unworkable idea. There are different fuel types. I hope you appreciate that now. Not all of them are easily burned at low intensity. In fact, most are not. Those fuel beds have been altered by grazing, logging, and the invasion of plants. There are impacts from those burns to smoke and potential property damage and resource loss. It would probably require 2 million at least. I've seen estimates of 8 and 10 million acres per year to burn in California to keep up with the supposed fire rotation interval, which sometimes may not be accurate. It will not eliminate fires or bad fires overall, because as you can see, even relatively lightly loaded fuel systems can burn under severe conditions, and in any case would be a huge and expensive program to operate. So, in a nutshell, the bad news, in my view, it is not and never was this simple, this fire here, over all of California, all of the time. The good news is fuel modification, including prescribed burning, can do some really good things, ecologically good things, reducing hazard, and especially in well-placed zones that are going to be strategically helpful in preventing loss of people's homes. And the homes themselves can be made much more able to survive wildfire. So, and poor Smokey takes a beating as being the one that's caused all this trouble oftentimes, but Smokey the Bear was never anything more than a fire prevention message, saying that we shouldn't have carelessly caused accidental fires, and keeping people from stupidly lighting fires is not what caused the fire problem. And one way or another, fire control is still going to have to be part of the picture. You're not going to burn your way out of having severe fires. This has been quite a long discussion. I hope it's got you thinking about some things. In any case, if you're still with me and you haven't gone to sleep and you haven't gone and had a glass of wine, thank you for your patience.
Jim, thank you very much. This is profound and a huge amount of information to digest, and really appreciate you sharing your expertise with us. It provides such a different view of the problem. There's a part of me that is almost fatalistic in response to this, that under the right conditions, there's nothing that can stop a certain fire. Is one of the is that a correct response?
Yeah, I think, you know, if it's really dry and really windy in any fuel system we have, a fire can move fast and be difficult to stop.
A lot of mitigation can happen.
But as my helpful wife reminds me, you can mitigate that quite a bit, and not the least of those are making homes much less vulnerable. But it's, you know, maybe the desert that didn't get invaded by grass, but sooner or later, almost any of it can burn.
And try and prevent some of the human caused emissions.
Yeah, fire prevention doesn't hurt. You know, it's not, Dave, it's not as if you have to have it no matter what, or you can get rid of all of it. It's a matter of shifting the probabilities of large severe fires lower and lower, recognizing that there's no perfect solution, at least within the confines of cost and lifestyles and so on that are important as well. Yeah. So that's kind of a wishy-washy non-answer, but
yeah, I think you know, in working with the new Fire Prevention Authority and Fire Safe Marin, one of the major messages is the most important thing to do is to fire harden your home, and your presentation certainly emphasizes the importance of that you need to do what you can do. Now, those of us that have wooden homes have a serious problem in that regard, and but that is probably the direction we all should spend a lot of time on.
Yeah, and you can do a lot. You know, if you don't have openings that firebrands can go through, and you don't have anything flammable for them to land in, and you've treated the fuels well enough that you're not going to have a 60-foot flame front within 20 feet of your house has probably got a very good chance of making it.
You know, there's a lot of emphasis on vegetation management, and your talk provides kind of a palliative as in terms of the modest expectations from that vegetation management. And I just wanted to see if you comment on that.
Well, I hope, I really believe, and I hope I made the point that it is not the cure-all. It's a useful tool, and it can do some nice things ecologically. It can do some very helpful things in terms of strategically placing fuel breaks so that homes are easier to protect and are less at risk. And that's all to the good. But it gets portrayed as a panacea. And so it isn't an all-purpose panacea. If only we had done it that way, we wouldn't have any of this trouble. It isn't that simple, but it can be very useful.
The question in the chat is, what were the conditions that made cultural burning successful before European arrival? Where was it used traditionally, and what times of year, et cetera?
You know, I would like to have more facts for that answer. I think, to be quite honest with you, that our picture of it is perhaps a little bit idealized. It's based on people saying things that they heard from the past. My guess is that, in fact, this aligns with some information that is also publicized about the rest of the Intermountain West, in the mountainous West, is it was done fairly selectively. Areas that were perhaps used for game hunting or acorn harvesting or basket making materials or routes of travel or strategically placed areas that they want to have open so that the approach of enemies or something could be detected. Those were much more often burned than just generally putting fire over all the millions of acres of the landscape. They probably were fairly light fuels that were bordered by natural fire breaks, maybe a river, maybe a rocky slope. And you can do spring burns in the dry fuels if you had fairly low humidities and the foliar fuel moistures are still quite high, so there's not so much danger of torching out and crown fire. Natural barriers like streams, like rocky areas, like sparse fuels, and either in the fall, late enough that they don't have time to get anywhere before the rains come, or in the spring, and they'll go out at those natural barriers without involving the overstory fuels. That's my picture of the kinds of places they probably burned more often, and it wasn't just uniformly spread across the landscape. It was very focused to provide certain, beneficial results.
Yeah, another question is, where can one find experts to help manage local conservancies? I would just comment that if we're talking about the public land management agencies, they all have natural resource managers that have been given, I believe, responsibility for working on fire safety as one of their missions.
Yeah, the agencies have tons of people, and you could answer that question as well or better than I can. I don't know that side of it especially well. Agencies and conservancies, and they would even probably be willing to comment in more general ways on things that maybe lie outside their jurisdiction, at least as an advisory and not, an official consultant.
I think we have time for one more question, which I see in the chat. Was the mean fire return interval different before the arrival of humans to California? For example, more than 100 or 150,000 years ago.
Yeah, that's a great question, and I have no clue, except, humans could only add to the fire frequency. They didn't subtract from it. So maybe it didn't add much, especially when there were relatively few people, but over time, it probably increased fire frequency. And us modern day humans, we're pretty good at putting out fires, but we're really good at lighting them. So we haven't necessarily seen a reduction in fire frequency. In some places, we've seen some reductions in acreage, but not huge. So, I'd love to know tens of thousands of years ago what was happening. I just don't. And since most of the evidence is from tree ring damage, it'd be hard pressed to have direct evidence of fire frequency in any specificity or detail that far back.
No. This will be the final question. Is there any correlation between population density and occurrence of wildfires and their severity?
Well, certainly their occurrence. If you look at a map where the fire prevention folks have plotted fire ignitions, they map out quite nicely around population centers and along roads. Are they more severe? You know, I guess part of that answer would be the more fires you light and the more extended period over which you light them, the more you raise the odds that severe conditions will drive a high intensity fire. So a reasonable assumption is that they have increased, but there's no question that the clustering of fire ignitions, it maps very nicely over human activities and where they do things.
Well, Jim, I want to really thank you for a fabulous presentation that is sobering as much as informative, and it certainly informs all the work that we're doing with the Fire Authority and others in Marin County on our own fire safety issues, and all of us individually as we think about our own homes. I want to, while I have you for a moment, I want to tell you about next month's program on March 8th, the second Monday. Tom Burns is going to be talking about mycorrhizae. We're going to be talking about what's under the surface, that complex and often little known part of the native plants that is so important to their survival. So we hope to see you next month at this same time. Thanks again for attending.
Good night.